Welcome to Lecture 17 of the course Agricultural and Biosystems Structures Engineering. Again, I'm Ian, and we will be talking about the defects or the defects and the ways to improve or to counter these defects in the components of our agricultural and biosystems structures. We will proceed first with the defects uh, of materials of construction as they are in the service conditions. Okay, so defects are imperfections or flaws, similar to the way people and other naturally occurring things have theirs, and these are caused by aging, okay, the natural deterioration of materials. Again, they are at least stable at some point, and they deteriorate by wear and tear. Then there's also a physical or a human factor of faulty construction. Now, it's very important to know, okay, the imperfections and flaws or the defects of buildings, because again, um, this may lead to loss of life and properties. So it is important to address these defects, and we have these steps. We diagnose the symptoms, okay, and understand the possible underlying causes of those defects, and then carry out timely repair and maintenance works to maintain good structural condition. It is important to take note of the previous concept presented in the class, where um, it is important to design, okay, to never over design the structure, okay, because doing so, okay, the concrete, okay, will fail miserably or without warning, so that only the steel will be left in the or safely within the limit. And in that case, okay, without warning, the structure may fall apart. All right. So there are other cases, but it is important to know of the defects, and let us go through them one by one. Right. We have here the types of these defects. Okay, you have non-structural defects or cracks. Anyway, it's cracks, and the cracks is stretching in many directions. If you could see on the image, okay, the cracks appear between non-structural walls and structural members, and they actually appear as hairline cracks. And this is the least of concern if ever there are in a building. And then there you have your spalling or spalled concrete. The parts of the surface chips or peels or breaks away. Okay, that is in the bottom. Okay, the water or rust stains on the surface, or water seeps through the wall, and the surface also bulges. The concrete peels off and exposing the rusty reinforcing bars. So based on those just those descriptions would give you a very the very idea of what to see, because they are very visual. Okay. Now there are causes of concrete spalling. You have here corrosion inside the reinforcing bar. Okay. There's also water seepage, and well, the water is causing that kind of corrosion. Okay. The excessive moisture is due to the ambient conditions. Okay. The air could be um, too humid. Okay. There's also alkali element in the concrete. Okay. There's sulfate attack, and then there is acid rain. Now, to prevent this concrete spalling, you have to provide adequate concrete cover. Okay. Paint is one. Avoid excessive water content. So later in the class, the right mixture of water and aggregates is important. Okay? Aggregates and cement. Okay? There's also the applying good water sealant on the concrete surface if the structure or that portion of the structure would be encountering um, heavy water from time to time. Okay. Using also one is epoxy coated reinforcing bars. Okay. Now let's proceed to other cracks. Okay, you still have here number 3, structural cracks, and they penetrate the surface into the structural portion of the concrete compared to non-structural cracks. Okay, this is of serious concern. Okay, and this is focusing already on the structural elements, and there are usually long cracks across the wall and rusty stains appearing on the cracks. Diagonal cracks on corners are shown. Okay, that is a kind of a structural crack that is of serious concern because that is in a door frame. Okay, uh, you have here also, last but not the least, you have defective external wall finishes. Probably this is the least, along with the non-structural cracks. This is one of the least of concerns, and probably the very least of concern, because that would only involve well, finishing again the wall. So there's the bonding of the finishes or the tiles from the wall, causing hollow sound, and there is cracking of the wall surface, bulging with a hollow base, the falling off of the finish, okay, or the finishing is very loose. Okay. Now, what are the actions to correct this concrete defects in buildings? You have to clean the area and remove the loose concrete, especially our example of which is the spalled concrete, and surface chipping, and then rebar cleaning. You have to clean the rebar, and then concrete casting and application of curing compound or water curing, and then finally finishing off and painting. So I've seen this work out in construction, and this is what actually they do to preserve the integrity and the structural integrity of the building. Now let's proceed to the rebar. Okay, I mean this is the very center of concern in concrete, okay, reinforced concrete, because rebars are what give the concrete uh, the tensile strength, right? So one of the topics here is strengthening of metals, and uh, this is of concern because again the rebar is the tensile strength provider for the or the source of tensile strength for the concrete. And shown on the screen is the spark test for various steel metals. You have for low carbon steel, mild steel, medium carbon. Again, steel is an alloy of iron and carbon with the different names, so from low to mild to medium to high, gray cast iron, identifying the degree of carbon concentration. And later we'll see what this means. Now, if you do a spark test, that is grinding the metal, okay, again, you have to push the metal towards a grinder. And when you do that, okay, you see a spark, and on the left, you see the different kinds of sparks, or shafts, forks, appendages, brake arrows, and then sprigs. And for the individual sparks of the different types of steel metal, you have there at the most left, your die steel, HES, okay, high alloy steel, okay. You have the volume of stream and the relative length, color at wheel and color at end, and the description. So you could see that of these two, they know that the color is different, but this is how they should look like. Okay, just make sure that the color is actually as they are, as presented. Okay, but in here it's all, I think, yellow. I'm not sure. I'm actually colorblind. But then anyway, so you just have too much. You could take a picture of that spark test and compare that here to this test and know what kind of metal or steel metal that is. Right. So other metals would have also their own sparks in a grinder. Okay, against a grinder. Okay, when you conduct a spark test. Okay. Now, it's important also to take note of the different steps to strengthen these metals, and we do so. Okay, you have here work hardening. This is a physical method, the only physical method among the the choices or those that are going to be presented or the options to strengthen metals. This is increasing the strain of the material by introducing stress. And this, of course, by dislocation movement and generation in the crystal lattice structure of the material. If you could see on the right, you have here the different crystal lattices for metals. You have body-centered cubic, face-centered cubic, and hexagonal pushback. So these are metal structures. Metals are, but they have the metallic structure. So with this, okay, with work hardening, okay, there is dislocation and generation of structures. So they are forced together. So that strengthens the metal. And this is good for metals such as iron, since iron is a metal with high melting point and is non-brittle. One example of work hardening as it happens in fabrication is via machining. So when you machine metals, there is work hardening. Next up is alloying. Okay, that is actually solid solution strengthening. Okay, this is adding atoms, pure atoms of another elements to the steel, to the metal. Okay, one example is brass, which is copper and zinc, and other is, well, steel is an alloy. Okay, so that's solid solution strengthening. Your precipitation hardening. This is heat treatment to increase the yield strength. And another is dispersion strengthening. This is alloying with small oxides. Okay, introduces a second phase to the metal. This is also common in steel. Okay, changes the crystalline size, and also you have here grain boundary strengthening. Okay, it's changing the crystalline size. Sorry, changing the crystalline sizes for the grain boundary strengthening. Okay, transformation hardening. Last is you have here. This is for martensitic strength steel. So this is done by the rapid quenching. So same with precipitation hardening, it uses heat, but in transformation hardening, there is rapid quenching, rapid cooling of the metal as it cools down, right? So this changes all of I mean, the except number one, which is physical. The others also change the physical structure of the concrete. Let's see how, or the concrete, the steel, okay? Let's see the various phases of steel, okay? And here it is, right? So this is the iron carbon phase diagram, and based on the temperature and the percent of carbon, okay, one could achieve the various phases of steel, and it would create a different steel because of the different structures of the crystalline lattice structures in the metal. There would be a lot of differences in the properties. So you have here your eutectoid steels, okay, with carbon content from okay, you have a carbon content from 0 to 0.83. You have your eutectoid steel, okay, eutectoid point, and then you have your hyper-eutectoid eutectoid steel, okay, and then you have your cast irons also in here. There's also your austenite, okay, cementite and perlite and ladybirite. Cast irons actually consist of eutectoid cementite, okay, over here. Yeah, sorry, here, eutectoid, and then injected from austenite. It's here, sorry, eutectoid cementite, okay, it's here, and transformed ladybirite. So it's a combination of such. Okay, ladybirite in which austenite is transformed to perlite. So it's a combination. Okay, cast iron is actually over here. Okay, and then other steels, okay, which with very high temperatures would lead to cementite and austenite, and there's even a liquid phase already. Okay, So mild steel is hyperotectoid, your tool steel is hyperotectoid. Okay. Now, there are other metals, and allotropy is the ability of a material to exist in two or more crystalline forms, as steel and iron does. Okay, you have your alpha iron, your body-centered cubic. You also have your other phases, right? FCC and BCC. Okay, and at 768 degrees Celsius, iron loses its ferromagnetic properties. Okay, so it depends on the temperature. Okay, the temperature changes the crystalline forms of the material. So you have here forms, okay, forms of ferrous metals. You have your cast iron, and you have a gray cast iron, okay, and also your uses. This is actually a review of the materials of engineering. Okay, gray cast iron or gray iron graphite exists largely in the form of flakes, and there's negligible ductility, and there's this is weak in tension used as machine tool bases. And your cast iron under our covering ductile cast iron, nodular iron, graphite is nodular or spheroid form, ductile and shock resistant. The graphite flakes exist in nodules by addition of magnesium to the molten metal prior to pouring. So again, this is already an alloy. So an alloys of three metals. Your marginal cast iron is white cast iron are milled in carbon monoxide and carbon dioxide at a temperature of 800 to 900 degrees Celsius. Cementite then decomposes into iron and graphite and exists in clusters in a ferrite or pearlite matrix. So again, cast iron is you have your ledeborite, pearlite, and cementite phases. Okay, structure gives material ductility, strength, and shock resistance. Your white cast iron, this one's very hard, wear resistant, but brittle because of the presence of large amounts of iron carbide instead of the graphite, and obtained by rapid cooling of gray iron or by adjusting composition by keeping carbon and silicon contents low. There's also a compacted graphite iron is in the form of short, thick, and interconnected flakes with undulating surfaces and rounded extremities. The mechanical and physical properties of this is it's intermediate between flake and nodular graphite cast irons. Next, you have wrought iron. Okay, iron heated before being worked with tools to shape it. This is wrought iron. It has very low carbon content, almost negligible at 0.08%. Okay, characteristically fibrous in appearance, but compared to cast iron is softer and more ductile. One use of wrought iron is in decorative fences. Okay, because this is very low. It's high. It resists fatigue, and then it has high tensile strength than cast iron because it has a lot of iron in it. Okay, the uses of steel. You have your dead mild steel. Okay, the uses, and the steel would vary in carbon content. You have your dead mild steel, medium carbon steel. Okay, in between them is the mild steel, and then their applications. Okay, this is just to show their uses, but again, mild steel is used for rebars. Okay, rebars, also for structural works. Okay, you also hear your medium carbon steel, right? Oh, what happened here? Anyway, sorry, that should be out of the picture. Anyway, you have here a medium carbon steel, shafts, gears, railway tires, and then for high carbon steel, these are for very high temperature and high pressure settings, such as your blocks, okay, chisels, okay, forging dies, railway rails, okay, springs, even, of course, and most springs that are used in industry. Okay, you have your knives, access picks, because they are now should be very hard, okay, resisting high pressure and high temperature. So very high carbon content. And then you have a high carbon steel, and this is for ball bearings. Again, very high strength applications, or requiring hardness. Okay. Now, the uh, range of the carbon concentration is between uh, 0.3, okay, and then 0.6. Okay. 0.3 to 0.6 is medium carbon, but beyond 0.6% is high carbon steels. Now, there are also non-ferrous metals, and this 20%, less than 20% of the metals in industrial products, but they are also still very important, and to take note of them in relation to the topic on strengthening of metals, because they are they are used also in alloying. Okay, so most of these metals, non-ferrous, they are lacking in structural strength, and they are only getting the strength because they are, or having the structural strength because they're alloyed with, well, iron, for example. You have also them resisting corrosion. Okay, that's a good thing with these metals, and they have good electrical conductivity, and they're easy to fabricate. They're also high thermal conductivity. Okay, they allow, or they transmit heat easily. They're very low disease, and more expensive than ferrous metals. But there are one good thing is they have a lot of color choices. So one is aluminum, and this is the principal properties of 99% of aluminum. Okay, this is as shown. You have your melting point, crystal structure, the common one. Okay, density, Young's modulus, the tensile strength, the electrical resistivity, the corrosion resistance is identified here in the table. This is used for containers and packaging, building, and other types of construction, and also for transportation. Likewise, in electrical industries and consumer durables. And the utilization is in cold working or plastic deformation at regular or ambient room temperature, around 24 degrees. Okay, nickel. This is a silver white metal and used in alloying addition in many steels. Okay, this is the one used for stainless steel and cast irons also. Chemical engineering plants in food industry have high use for this because of its high corrosion resistant, and also yeah, it's the food grade material of choice in the food industry. You have your electroplating use as well. Okay, and the properties are shown. Okay, melting point, crystal structure, density, Young's modulus, electrical resistivity, and the corrosion resistance. There are also alloys of nickel with focus on it. Okay, with I mean, this is the major component. So you have your Monel, single phase alloy, high corrosion resistance, and used for steam turbine blades. Inconel, okay, good properties at high temperatures, either sheets for electric cooker, 80% nickel, 40% chromium, and 6% iron. The mnemonic series, okay, 55 to 80% nickel and 20% chromium. High temperature creep resistance, gas turbine discs and blades, and also for flame tubes. You have your zinc. It is a bluish white metal. Okay, excellent die casting material because of its low melting point. Thus, okay, used in die casting. Okay, you have your metal forced into a die cavity of this material, ranging 0.7 to 700 megapascals. Okay, the properties. Okay, melting point, crystal structure, density, Young's modulus, electrical resistivity, and the corrosion resistance is good. Okay, this is HCP compared to the previous two, which are FCC, okay, or face-centered cubic. Okay, tin, okay, exists in two allotropic forms. Again, remember allotropy. You have your alpha and beta diamond type crystal structure. You have your body-centered tetragonal structure. This is the first one is gray tin, the other is white tin. Okay. Used in coating of mild steel plate to make tin plated cans. You have also the manufacture of white metal bearings. Properties, melting point, sorry. Crystal structure, density, Young's modulus, tensile strength. You have your electrical resistivity in ohms. Then you have your very good corrosion resistance. Again, this is body-centered tetragonal in structure. I think this is the most common, okay, the white tin. Your magnesium, okay, low density, most important property. Okay, this is very low density, weak and low ductility, and thus it is used for aircraft construction, motorcycle wheels, engine crankcases, sacrificial anode material for ship hull protection against corrosion. Okay. You have your properties. Melting point, I think it's low than most, 649. Oh, it's just enough. Okay, it's actually high. Sorry, melting point is high. You have your HCP, hexagonal. Okay, crystal structure, the density, okay, kilograms per m squared, m cube. This is very low, 1.74 times 10 to the 3. Young's modulus at 44 gigapascals, electrical resistivity, and then very good corrosion resistance. You have your titanium. This is generally expensive metal, but high strength and low weight, and also used in aircraft construction. You can see the density is 4.53 times 10 to the 3. You have your structural forging workpiece is forced through dies and tools by compression. Is also used in chemical engineering plants because a very good corrosion resistance, okay, and still lightweight. The melting point is very high at 1660 degrees Celsius and exists in two phases: the alpha HCP and then the beta BCC, body-centered cubic. Okay, lead, okay, soft and malleable. Lead is one of the reasons of the decline of the Roman Empire because this is very easy to work on. So this was used by the Romans to in their public pools. Okay, and that was a way that they were able to intake the lead, and then causing the sterility of the people who go to the pools. So the lower fertility is causing the decline. It caused the decline of the empire because there were fewer people being born. Okay, uses lead acid storage battery. Okay, well, this was also used in as an anti-knock agent in gasoline, okay, in the form of tetraethyl lead or TEL, and it was also banned because that's why you have your unleaded gasoline, because lead still is a poisonous. Okay, it's a hazardous metal in the air for humans, again causing that sterility. You have also your weather flashing in buildings, okay, radiation shielding due to high density. Okay, very high density at 11.34 kilograms per m cube. A melting point quite low at 327 degrees Celsius. Crystal structure is FCC. You have your Young's modulus and electrical resistivity, and corrosion resistance. That is very good. Copper, principal ores of copper. This is a mixture of copper and iron sulfides, and this is produced by smelting or electrolytic extraction, and you achieve a 99.5 to 99.8% purity. You have the properties here presented, and on the right, and the uses are for wires. Actually, this is the cheapest material to be used in wires. That's why, well, actually, gold is the most best conductor, but it's very costly. Okay, while copper is cheap, okay, and readily available. You have your architectural cladding, okay, water tanks and vessels, also for tubing of heat exchangers and air conditioning, okay, and other heaters, for example. So very good corrosion resistance. Electrical resistivity is, well, it allows conductivity, okay, good conductivity of electricity. Young's modulus, okay, it's quite high. You have your density and your crystal structure. Very high melting point as well. Now, copper is available as brass, again, copper zinc, as a while ago, as was said, okay, increasing the ductility of your bronze, aluminum bronzes, cupronickel's beryllium copper, highest strength copper alloy. Okay, you have your cadmium copper and then the chromium copper, okay, high-strength electrical and thermal conductivities and uses in spot and seam welding electrodes. All right, so that would be all. I will be seeing you in the next lecture, where the topic is on the laboratory and other tests that could be done for the testing of metals and other materials of construction. I'll be seeing you by then, and thank you for listening.